So students, today we are going to discuss data encryption standard and advanced encryption standard of the security. So these two are very important topic, and as earlier we have discussed that in order to ensure the confidentiality, we need to encrypt the messages, right? And the messages can be encrypted in variety of ways. So before that, we need to decide that in what way we are going to discuss in what way we are going to perform the process of encryption. So the encryption process can be performed either on a block or on bit by bit basis. So especially your DES and AES are based upon your block ciphers, or you can say these are the techniques of block cipher. Block cipher means we are going to encrypt on a particular block at a time. Okay, so that means we are going to first convert our messages into number of blocks first. Okay, and then we'll be performing the encryption on these particular blocks one by one. Okay, so this is why we call them as a block cipher techniques. So apart from that, the moment we have seen those classical encryption techniques, we have come to know that in order to increase the security, we have to encrypt multiple cipher texts at a time, or multiple alphabets at a time. Okay, so that we have seen in the case of your Playfair ciphers. So the moment you increase multiple alphabets at a time, those techniques are going to provide you the more security, because they provide more shuffling to the text. So whatever cipher text we get at the end, that uh, offers more security. So this is the idea which we have got from the earlier techniques. And apart from that, first we need to discuss the FISA cipher structure, which has laid the foundation for data encryption standard. So in this structure, we have got an input in the form of a data block and a key, and then the data block has been divided into two parts. The first one is called as the left part, and the other one is called as the right part. And then those two halves go through a number of rounds. So especially these two halves go to the 60 number of rounds, and in each round one of the part doesn't change, and on the second end, in the second part, one of the part go through the number of operations. Okay, so we are going to see how one part is going to pass, and how the next part or next half is going to be passed to the next level or next operation. So this is how your each and every round looks like in a physical cipher structure. So as explained, that your 64-bit block will be divided into two equal part of 32 bits each. So this one is your left half and this one is your right half. Each will be of having 32 bits with them. Okay, and as you can see, one of the half has been passed as it is to the next round. Okay, no changes have been observed in this particular part. So this right half has become the left half for the next round. Fine. And the left half is going through the number of transformations. And after having those transformations, it will become the right part for the next round. Okay. So as you can see, first the left part has been picked, then the content from the right part has been picked, then it goes through some of the transformations. We call it as a function. Okay, where we have the right part content and then the key, which is used to each and every round. So this function has been applied on this right half content along with the key to generate some new content, and these new contents has been mixed, right? And then the output of this mixer becomes the right part for the next round. So this is the basic layout of your Fizzle cipher structure. Okay, and this is the working of a single round. Fine. So in physical cipher structure, similarly, a similar 16 number of rounds have been performed, and at the 16th round, uh, it produced sufficient mixing, or you can say the text which you get at the end is your cipher text, and it stands well, or you can say uh, it offer good amount of security. Okay, and in order to get back your plain text, you need to perform the reverse operations. Okay, so this is the process of encryption, and this is the process of decryption. Okay, then of course these are the invertible operations, so the decryption can be derived from these rounds. Okay, so you can just have them as a part of your exercise. Apart from that, uh, your DES, as discussed, is depend upon your physical cipher structure. So let us see some of the details regarding your data encryption standard. So this is the most widely used block cipher technique in the world, and it has been adopted as a standard by NIST in 1977. And very similar to a physical cipher structure, it also offers 16 number of rounds, and it has got a block size of 64 bits with a key size of 56 bit. And how it offers security, it offers security with the app function, and this S function is comprised of your S boxes and P boxes. So we'll discuss what these S boxes and P boxes or E boxes are all about. So as we know that these are the block cipher techniques, so data will be divided first into number of blocks, right? So let's say this is your block, and then it goes through the encryption process, and then at the end you get 64-bit cipher text, right? And in each cipher, or in each process of encryption, we do pass or do provide some keys to it. Okay, and this key size is going to be a 56-bit. And these are the things very special regarding DES, and these are that it has to provide a good amount of security, and it has to be easy to understand. Apart from that, it should not depend upon the algorithm secrecy, and it should be adaptable to the diverse applications. So these were the objectives which have been kept in mind before designing any cryptographic algorithm. So the first objective has to be that it should provide good amount of security, right? And it should be easy. Apart from that, the most important thing that no matter if the algorithm is known to the adversary, even after that, the adversary must not be able to crack the ciphertext. So all secrecy has to depend upon your key only. Okay, so no matter if the adversary is knowing the encryption algorithm which we are going to use, or which one is going to use, so it should not, or the secrecy or the security of any encryption process should not depend upon the algorithm. So this is the some rule which we have discussed while discussing your classical encryption techniques as well. Apart from that, it will be good if the number of applications, or you can say if that algorithm is applicable to number of applications, then you can consider it as a good algorithm. Apart from that, it should be economical or cost effective for the hardware implementation. It should be efficient, and it should be easily validated and exportable. Means minimal in size. So these are some of the things regarding any algorithm. Okay, and DES have all these things in his pocket. So let us come straight forward. So it depends upon your substitution permutation algorithm, and it has got 64-bit input and output block, and the key size is going to be of 56-bit, and it goes through 16 number of rounds, right? Apart from that, the special thing about DES that it offers very high throughput. Means it can be run very fastly. So in numbers, it can provide you the throughput up to 100 Mbps. Apart from that, it is also very cost effective when you go to implement it in the hardware. Apart from that, it is also very good for medium security applications. For example, your speech communication, your image communication, or your multimedia communication. So in all those sort of applications, DES and AES are considered very good because they do offer very good rate of encryption and decryption. Or in other words, we can say very fast encryption and decryption can be done. So this is the basic overview of your DES. So first some initial permutation has been performed, and then the output text goes through the number of rounds, especially they goes through 16 number of rounds, and then at the end of 16th round it goes through a swap, and then a final inverse initial permutation is performed. Apart from that, each round do get a special key ranging from K1 to K16, and this key is also different for each and every round. Okay, however, the input key is a single key or the same key, and from this particular key, different keys are being derived for each and every round. Okay, so we'll see how different keys are going to be derived for each and every round, and this is basically done through some particular processes. So we will see in detail in the coming slide. So the main idea behind the success of DES is the presence of diffusion and confusion. So if you talk about diffusion, that means you are trying to hide the relationship between the ciphertext and the plain text. Okay, so one should not be able to get the plain text by observing or by attacking the ciphertext. Okay, so your diffusion do this thing which hides the relationship between the ciphertext and the plain text. Apart from that, second one is confusion. Confusion means one should not be able to derive the key from the ciphertext. Okay, so it hides the relationship between the ciphertext and the key. So these are the basic two things which has laid the foundation for the success of DES. And these two things are being basically achieved with the help of S boxes and P boxes. So again, just the basic overview of DES has been given. So initially 64-bit plain text has been passed as an input. Okay, and in the key schedule 64-bit key has been passed, right? So after PC1, you can observe that 56-bit output is coming, right? And after PC2, 48-bit output is coming, right? So how these things are coming, we will discuss in detail. So this is the detailing of a single round. Now we are going to see what exactly happens in a single round. So this diagram gives the detailing of a single round. So first, your 64-bit input has been divided into two equal parts. Okay, we call them a left half and the right half, as discussed in the Fiddle cipher structure. So one of the half, which is the right one, becomes the left half for the second round. Okay, so there is no problem over here. And now in order to get the next half, we have to go through the number of transformations. Okay, now let us see what these transformations are. So first, your right part goes through a expansion table or the permutation table, and the input of this table was 32-bit, but the output is of size 48-bit, right? And then the XOR, or you can say the mixing, has been done of this 48-bit output along with the 48-bit key. Okay, and again the output of this mixing or XORing will be of size 48-bit. Then this 48-bit is passed, or you can say it goes through the S boxes, and then this S box produce the output of 32-bit. Fine. Then it goes through some permutation operation, and then this 32-bit output is then XORed with the left part to produce the final right part. Okay. So now we are going to see the details of each and every transformation. Okay, specifically the details of expansion box and S box. Okay. Apart from that, if you see carefully the key schedule, again, the key schedule is also divided into two equal parts, right? Two equal part of 28 bits each. Then each part goes through some shift operation, some left shift operation. Okay, and these shift operations are different for each and every round. Okay, and then each part goes through some PC2 operation as well. And after this PC2, we get the final key, which is going to pass to the output of expansion box for the XORing. Okay. So this is the basic functionality of a single round of DES. Now let us see the detailing of these transformations. So this is the initial permutation and the final inverse initial permutation. There is no significance upon the security of DES, and the persons who have designed the DES have failed to explain that why they have put this initial permutation and final permutation, which has no significance at all in the security. Okay, so they have just randomly placed the bit. For example, the at the first place we are going to get the 58 bit. Okay, and at the 64 bits we are going to get the 7th bit. Okay, so thus some random shifting has been done. Apart from that, this is the detail of your expansion box or expansion permutation and the permutation function. So let us see what happens in this. So if you remember, the input of this E table was of size 32 bit and the output was of size 48 bit. So what happens is that 32 bit input has been divided into 8 equal parts. Okay, so 8 equal parts of 4 bit each. Okay, these are 4 bits. Okay, 4 into 8 is going to be your 32 bit. Okay, so the input 32 bit has been divided into 8 equal parts. Okay, so each part will be having 4 bit. After that, we are going to append 2 more bit into each part. Okay, if we talk about this particular part, then 1 bit appended at the beginning, and from where that bit is coming, that bit is coming from the neighboring block. Okay, so this part will take 1 bit from this neighbor, and last bit it is going to take from this neighbor. Okay, so this is how this block of 4 bit will become the block of 6 bit. Okay, so this is how the expansion is being done. For the first block, this bit is going to be taken from this block. Okay, in a circular fashion. So this is how your E table will look like at the end. The first block, 32 bit, 32nd bit will be appended at the beginning, and the 5th bit will be appended at the last. Okay. For the second one, the 4th bit will be appended at the beginning, and the 9th bit will be appended at the last. Okay. So this way, your 32 bit input will become 48 bit output. Okay, so over here it will be 6 into 8, then it will become your 48 bit output. Okay, is that there, students?
Yes, sir.
Okay, now we are going to see the detailing of your S box. So in S box, if you observe carefully, that input is of size 48 bit, right? So this is your 48 bit input. Okay, and again we are going to perform some number of transformations. Okay, and for that transformations to have, we have got some 8s boxes, and how those 8 boxes have come into picture, that is again a very long issue. So those persons have taken around 8 to 10 years in order to design these S boxes, and how they have designed, they have not made it public. Okay, again, that is a very confidential matter for them. So they have not disclosed how they have designed these 8 S boxes. So each transformations have got its own S box. So in this DS, we have got 8 number of S boxes, and each 8 box will be having the input of 6 bit. Okay, 1, 2, 3, 4, 5, and 6. And at the end, they each and every S box will be producing the output of 4 bit. Okay, so let us see how do they work. So these are your initial 4S boxes, and the data which come as an input to these S boxes, from that data only we are going to derive the addresses to these S boxes. Okay, so let's say this is the input. Okay, input of your 6 bit. So the first bit and the last bit will give you the row number, while the middle 4 bits will give you the column number and row number of these S boxes. Okay, so let's say if the input is 1 1 0 0 1 0, so 1 0 will be the row number, and 1 0 0 1 is going to be the column number. Okay, so if 0 0 is the entry, we start from here 0 0 0 1 1 0 and 1 1. So this is going to be your row number for 1 0. Okay, and similarly you can have the address 0 0. Okay, then 0 0 0 1. So like this you will get the column number as well. Okay, so this is the 9th one. Fine. So after having the addresses, you will be getting one of the entry, for example 3rd for the 9th one. Okay, let's say this is the entry. Okay, this is the entry. So the output is going to be 15, and then you need to convert that 15 into binary. Okay, so whatever is the data, whatever is the entry you get at the end, you need to convert that entry into the binary equivalent. So the moment you convert that one into the binary equivalent, that will be having the 4 bits, right? So this is how you perform the operation on S boxes. Okay, so these are the your other 4 S boxes, and in total we have got 8 S boxes. Apart from that, if you talk about the key schedule, then if you observe, initially we do pass 64 bits, then we perform some parity drop. So in this case, the rightmost column has been dropped. Okay, after arranging it into 8 by 8. Okay, the rightmost column has been dropped. So the moment you drop this 8 bit, it will become 56 bit key, right? Then it is going to be divided into 2 equal parts of 28 bits each. Then some compression has been performed, right? And this compression is again nothing but dropping out some bits. Apart from that, if you talk about the left shift operations, which differ from round to round, so in the first round only the left shift by 1 bit has to be performed, and apart from this 1 2 9 and 16 you need to perform 2 left shift operation. Okay, that means that you need to perform left shift by 2 bits. Is that clear? And
Yes, sir.
in PC2, you just need to drop out some bits. So in the upper part, I have shown that in the upper part, we need to drop 9th, 18th, and 22nd and 25th bit. So you will find that these entries are missing from PC2 in the upper half. Okay, and similarly, some of the entries will be missing from the second half. So some bits have been dropped out. So this is how we perform the compression. Okay, so after eliminating 4 bits from the upper half and 4 bits from the lower half, so this 56-bit input will become the 48-bit output. Okay, and this is the schedule of left shift operations. Okay, so as explained in the first and second round, only bit rotations will be done by 1 bit, and in round number 2, 3, 5, 6, 7, 8, 2-bit lift, 2-bit left shift things are going to be performed. And again in 9th round and 16th round, only left shift by 1 bit is going to be performed. So this is how we generate different keys for each and every round. Okay. So at the end, we also need to understand the avalanche effect, completeness, and the strength and weakness of DES. So avalanche means if you are going to change 1 bit, then number of bits are going to be changed in the ciphertext. So it has to be there. Okay, and completeness means uh, 1 bit must depend on the many bits. Okay, and we talk about the design criteria. So design criteria of DES are designing of S boxes, P boxes, and their function, and the scheduling of the keys. So yes, we have already discussed this thing in detail. Apart from that, there are some weaknesses of DES are also present. So weaknesses are there in the form of the keys. So one need to avoid these keys. Okay, there are some weak keys which one need to avoid. Apart from that, there are some also semi-weak keys. So if you use these keys, then the ciphertext which we are going to get at the end will not offer the great level of security. So some semi-weak keys are also there. Then some possible weak keys are also there, which is normally listed in this slide. So we need to avoid the use of those keys. Okay. So since you guys have already studied these things in your BTech, so that is why I'm not discussing in detail. So is there any doubt in DS? If no doubt, then I will say
No, sir.
okay. Now, this second most important algorithm of cryptography is your advanced encryption standard. And this has been published as standard by NIST in December 2001. And again, the security criteria or the criteria which have been defined by NIST for selecting AES was security, cost, and implementation. Security means it must offer a great level of security, cost has to be less, and implementation has to be easy, right? And this is non-fissile cipher-based structure. And over here, the block size is of 128 bit. In DES, the block size was 64 bit. But over here, it has the block size of 128 bit, means the more data can be encrypted at a time. Then it uses 10, 12, or 14 number of rounds, means it can be used in the variety of rounds. And in each round, the key size are also differ. So if you're going for the 10 number of round variation, then the key size is going to be 128 bit. In the 12, the key size is going to be 192. And in the 14, the key size is going to be 256 bit. Okay, so it depends that how many number of rounds you are doing in the AES. So this is the general design. So before the number of rounds, some pre-round transformations is performed, and in the last round, some different thing is being done. So we'll see what that different thing is. And in each round, some keys, some different keys will be passed. Okay. Before that, we need to understand the data units used in the AES. So the data units are your byte. So as we know, the byte is consists of, or you can say the comprises of number of bits. Okay. So if B is written in the bold, then that means we are talking about the byte, and in the if they are not in the bold, then that means we are talking about bits. Okay. So that byte can be represented in a row or in a column. Okay. Apart from that, the word is comprises of 4 bytes. Okay. And then block is comprises of 16 bytes. Okay. Or you can say 4 words. So this is a word. Okay. This is also a word. This is a third word, and this is fourth word. Okay. So in a block, there are going to be 16 bytes and 4 words. And then you can write them in the form of a state like this. Okay. So this is how you can write them in the form of a state. Okay. And similarly, you can write them in the form of words as well. Okay. This is word 0, word 1, word 2, and word 3. Apart from that, yes, we likely come to the structure of your AES. So these are the very simple things. Means either you can derive from uh, state to this formation. So this is the formula. For example, if you just talk about how you can get the S00, so this is going to be B0. For S10, you are going to get B1. So let's say if you talk about the 4, okay. So if you, the moment you put 4, so the mode is going to be 0, right? And over here you are going to get 1. So 0, 1 is going to be there. This one. Okay. So you can just uh, put the values in this formula, and then you can find at which place of this state this entry is going to be placed. Okay. And similarly, the reverse formula can also be derived to place the details like this. Okay. And each plain text has to be converted into hexadecimal equivalent, and these entries are nothing but your hexadecimal numbers. So we'll discuss how exactly these things happen. So this is the basic layout of your AES. So first we create a state from the text or from the message, and then this state goes through the number of transformations, and these transformations are your byte substitution, shift rows, and mix column, and at the end we have add round key. So these are the basic 4 transformations which we perform in AES. Okay. Now let us discuss each and every transformation one by one. So in byte substitution, again one table is going to be used, and with the help of that table, let's say this is the table, okay, and this is the input. So what we are going to do, we are going to derive the address from this input, and this address will be picking the entry from this table. Okay. So if the input is 00, so this is the going to be this is going to be the output. So 00 will be replaced by 52. Okay. Or if the input is, let's say, 0A, then 0A will be replaced by A3. Okay. So this is how the byte substitution transformation works in AES. Fine. So this was all about your first operation. Okay. So each and every entry will serve or will provide you the address, and then you need to use this address. Okay. And from this table, with the help of this address, you will going to get the another entry, and that entry will replace the original one. Fine. Now, if you talk about the second operation, which is shift rows, and in this case, we are going to perform some shift operations to the input state. So in the first row, no shift operation will be performed. In the first row, one byte shift will perform in the second, 2 byte shift, and third row, third byte shift. Okay, we are starting the address from 0. Okay, so as you can see, there is no shift operation in the 0th row. In the first row, shift by one entry has been done, then shift by 2 entries, and shift by left shift by 3 entries have been done. Fine. Then in the third operation, which is your mixed column, one constant matrix has been used. Okay, so one of the column has been picked, then that picked column will be multiplied with the constant matrix, and then it will give you one column at the end. So that one column at the end will replace the original column. Okay, so this is the thing regarding the mixed column transformation in AES. Okay, so this will be fixed. And then, of course, whatever transformation which we have discussed, each and every transformation has got their inverse operations. Okay, so in all transformations are invertible. Right? So we will see in detail how exactly this AES works. But before that, this AES performs very well against your brute force attacks and your statistical attacks and differential and linear attacks. So these are also, or your AES also works very well against your differential and linear cryptographic attacks. Okay. So at the end, I will discuss the working in detail with the help of animation. Just so can you see the animation, guys?
Yes, sir.
Okay. So as you can see, um, as we have discussed that AES is a block cipher, so we'll be having some plain text, then we'll be applying some cipher key, and at the end we'll be getting some cipher text. Okay, so this is the process of encryption. So in this particular animation, we are going to see the process of AES. So over here, the encryptor is going to be AES. So first we need to arrange our input in the form of a state. So let's say if this is the input, then we have to convert into the equivalent hexadecimal number. Okay, so if this is the byte, then we'll convert the first byte or the first part as 3 hexadecimal equivalent, and this one as a 2 hexadecimal equivalent. Okay, so these are the hexadecimal number. You must need to remember this thing. So this is how the things have been arranged. Okay, so in each block, how many bits are there? 8 bits. Okay, so 8 into 4 you need to consider, and then we'll pass this input to the encryption process. So this is the basic layout, right? So before commencing or before going to the round, one add round key process is performed. Okay, we call it as an initial round transformation, and then these 4 transformations goes to the 9 number of round. Okay, and at the last, one of the transformation is missing. Okay, or you can say in the final round we have eliminated, or one of the round is absent, and that round is your mixed column. Okay, so for the uh, initial 9 number of rounds, we do perform all the 4 transformations, but in the final round we will not perform the mixed column operation. Okay, now let us see each and every transformations one by one. So this table will already be given, which is your X box. then one of the entry will be picked, okay, and this will serve as the address to this table. So this will give you the column, this will give you the row number, and this will give you the column number. So let's say the entry which has come out is D4, and this D4 will take the place of the original entry, and the similar transformation will be done for the rest of the entries to the state as well. Okay. Then the shift rows. Okay, so there will be no shift in the 0th row, and there will be shift by one position in the first row like this. Then the rotation by 2 byte, and the rotation by 3 byte in the last row. Okay, so this is the transformation of shift rows. Then the mixed column. Okay, so one of the column will be picked, and then the constant matrix which will be given. So the moment you multiply this one with this constant matrix, the resultant column will take the place of the original one. Okay, so this is how the mixed column transformation is performed in AES. Then add round key. Okay, so one round constant will also be provided, and what you need to do, or what happens in AES is that one of the column will be picked, and that will be XORed with the uh, corresponding column in the constant round key. So this is how things are being done in the add round key. Okay. So these are the things which will come out after each and every round. Okay, so these are the outputs. And as we know that in the last round, mixed column operation is not there. So that transformation has been missing in the 10th round. Now this is the most complex process, so just see carefully. Now we are trying to derive the key for the next round. Okay, so let's say this is the key. So what has been done, that the last column has been picked out. Okay, and then one circular lower shift has been performed. Okay, thereafter byte substitution from the provided S box has been done, right? Then the first column has been picked, and one conventional column from this fixed matrix has been picked. Then the XORing of all these three columns will be done together to produce the final column, and this will take the entry. Okay. Thereafter, this process is a special one. Okay, and it does involve a lot of efforts, but generating the rest three columns is not that much complex. Okay, so for the next entry, this one and the second column. Okay, if you just form a square, then these two entry will come out. Then you just need to XOR them, and then the result will take the place of the next column in the next key. Okay, the similar process will be done for the third column and the fourth column. Okay, so thus there is a special thing about the first one only. Fine. So similarly, for the next round key, again the last round, the last row will pick one shift by the one circular shift will be done. Then byte substitution will be done, right? Then one of the column from the outcome matrix will be picked, and the first column from the last key will be picked. Then these three will be XORed together to produce the final entry for the next key schedule. Okay, so this is how things will be done. So you can say the keys are being derived for each and every round in AES. Okay, so is there any doubt? Then you can ask.
No, sir.
Okay. So apart from that, there is one more thing which I just need to discuss. Apart from that, you would have studied asymmetric key cryptography as well in your undergraduate program. So what happens in asymmetric key cryptography techniques that we use a pair of keys. Okay, so what do you mean by pair of keys means we use two keys and we call them as a public key and private key, if you remember, right? So let us come straight forward. Yeah. So this is the model of your public key cryptography. So over here we use a pair of keys and those pair of keys are nothing but your public key and private key. So what happen is, let's say this is the message which we want to encrypt. So this message will be encrypted with the help of a public key. Okay. And after encryption with this public key, only the person who will be having or who will be holding the private key will be able to decrypt the message. Okay. So let's say in this model, uh, at this end, this person is holding the public key of Joy, Mike, Alice, and Ted. Okay, so this is Bob, and Bob is having the public key of Joy, Mike, Alice, and Ted. That means Bob can send a message using the public key of Joy, Mike, Alice, and Ted. Okay, so Bob can send the message to this many person. Fine. So if in case Bob has encrypted the text using the Alice public key, then in that case only Alice will be able to decrypt the text. Okay, so decrypt the ciphertext. Fine. So number of persons can hold the public key, but only one person will be holding the private key, and whoever will be holding the private key will be able to decrypt the associated ciphertext. Okay, so this is the model of your public key encryption process. These are differences. I guess all of you already aware about this one. So I'll discuss RSA only. So in RSA, this is the process of encryption, okay, and this is the process of decryption. So this is your public key, and this is your private key. So if in case there is adversary who has access the ciphertext in between, so in order to get the plain text back, he need to solve this particular thing. Okay, means eth root of the ciphertext, which is very complex process. Okay, so it offers polynomial complexity in short. So this is the process of encryption, decryption, and key generation. And as you can see that the text is using one of the key to generate the cipher key. Then what has been sent to the public is the public key. Okay, then the cipher text will be sent to the other party. And then after getting the cipher text will be raised by the D, which is the private key. And this private key will be available with Bob only. Okay. So this is how the things are being done in RSA. So the most important thing in RSA is the key generation process. Okay. So as you already aware regarding this, first we need to take two large prime numbers. Let's say two large prime numbers are P and Q, and you need to choose these prime numbers such a way that they are not equal. Okay. Then you need to apply them to generate a number n. Okay. Then a Euler-Tauschant function called as phi n will be calculated. Okay. And this is how it will be calculated. So it will be p minus 1 into q minus 1. Okay. Then to generate a private key, you need to choose a number in between 1 to phi n, which is co-prime to phi n. Okay. So let's say if phi n has been 60, then you need to choose a number in between 1 to 60. Okay. So let's say it may be 3, it may be 7, it may be 13. So it is up to you. But the one thing which has to be there, that it has to co-prime with 60. Okay. Then you need to calculate the inverse of that E. And that inverse number is going to be your private key. Okay. So D is going to be the inverse of E modulo phi. So this pair is going to form your public key, and this D will become your private key. Okay, so this is the key generation process. So the things are very complicated in real world. So this is how big can be P and Q, and you already aware about that the factorization is a very complex problem. So it is easy to calculate P into Q, but if a number is there, let's say n, which is the product of P and Q, so it is very difficult to find out a value or a prime or a value P Q from the product. Okay, so finding out the factorization of two prime numbers is very difficult, right? So just one thing. Yeah. So one example has been given. Let's say two prime numbers 17 and 11 has been selected. Then first we need to calculate n, which is the product of P and Q. So let's say it is 187. Then you need to calculate the phi n unit Gaussian function, which will be 160 in this case. Okay. So after having this 160, we need to select one of the key, okay, which has to be co-prime with 160 or your phi n. So in this case, E has been chosen as 7. Okay, then you need to find the inverse of this E such that it produce 1 when have the mod 160. Okay, so let's say D has been chosen. So the moment you multiply this 23 with 7, you will get 161, and then when you get the mod with 160, it will produce 1. So that means D is the inverse of E. So with this D and E, your public key is going to be 7187 and your private key is going to be 23187. Okay, and this inverse can be calculated using Euclidean inverse algorithm. Okay, so this is the process of encryption. So this was E and this was D. Fine. So I hope you would have got the idea regarding the public key crypto system and your DES and AES. So in case if you guys have any doubt, any problem, then you can ask. Otherwise, I'll end the class. Students, any doubt? Any doubt, students?
No, sir.
No,
No,
sir.
sir.
Okay.